This is the worst weapon evolution ever built, and that is the secret of its genius. It is far too long to be strong. Basic physics says a blade stretched this far should be almost powerless. Lengthen any lever, and you bleed away the force at its tip. Yet this creature uses it to seize rivals, hoist them overhead, and hurl them into the dark. From the front, it looks like the antlers of a stag bolted onto an insect. But these are not horns at all. They are jaws. And how they cheat the laws of leverage is a masterclass in engineering. Meet the European stag beetle, the largest beetle on an entire continent. A male can stretch to 75 millimeters, much of it pure jaw. He is a tank that flies, clumsily, through warm summer dusk. But the real marvel is not his size. It is the problem hidden inside his head. Every engineer who has ever designed a robotic arm has fought the same battle he has. Reach further and you lose your grip strength. Grip harder and you lose your reach. This is the oldest trade-off in robotics, and a beetle solved it before we had the word. To understand the answer, we have to take his head apart. Start with the weapon itself. Those curved jaws are mandibles, the same mouthparts a smaller beetle uses to chew. Here, sexual selection has blown them up into antlers built for war. Only the males carry them. The females stay compact, with short, sharp jaws. And here is the first twist in the story. The female's tiny jaws actually bite harder than the male's monstrous ones. Her short blades sit close to the hinge, where leverage is strongest. His long blades push the cutting edge far from the pivot, into the zone of weakness. So the giant weapon that looks lethal can barely pinch a human finger. It was never built to cut. It was built to grab, to grapple, to wrestle. Picture two males meeting on a branch at dusk. They rear up, jaws spread wide like rival cranes. Each tries to slide his antlers under the other and clamp down. The winner is the one who can lift, and the loser is thrown from the tree. To do that, those long jaws still need a serious grip. And this is where a lesser design would simply fail. So how does a creature build force at the end of a hopeless lever? The answer is not in the jaw. It is in the head behind it. Look closely, and the male's head is grotesquely wide. That width is not decoration. It is structural. Inside, The muscle that snaps the jaws shut has swollen to enormous size. In stag beetles, it can be nearly 4 times larger than a female's. A bigger motor packed into a wider chassis. But raw muscle is only half the trick. The wide head also lengthens the hidden lever the muscle pulls on. Engineers call it the input lever, the short arm on the inside of the hinge. Stretch that inside arm and you claw back the advantage the long jaw gave away. It is the exact balancing act a mechanical engineer runs in a load distribution simulation. Long arm out, long arm in. Force traded against force until the maths works. The beetle computes this with chitin and muscle, not software. And the muscle stays aimed in the one perfect direction for maximum pull. Nothing is wasted. Every fiber points where the force is needed. Now add the next problem. Lifting a struggling rival does not just squeeze the jaws, it twists them. The weapon is loaded in bending and in torsion, the way a crane arm is stressed. A brittle jaw would snap at the worst possible moment. So the cuticle, the beetle's chitin armor, is built unusually thick. Its cross-section is shaped to resist twisting, like an engineered structural beam. This is the same logic behind the load-bearing frames in bridges and aircraft. Material in the right place, removed everywhere else, tuned for the forces it will face. Researchers have even run the beetle's jaw through finite element analysis. That is the same simulation software used to design car frames and turbine blades. The verdict? The geometry is tuned almost exactly for the stresses of combat. A weapon, a lever, and a load-bearing structure, all in one organic tool. And we still have not seen it do the thing it was truly made for. Back to the branch, and the fight reaches its climax. One male drives his antlers beneath his rival and locks the inner teeth tight. Now the swollen muscle fires, the wide head anchors, and the long jaws hold. The grip clamps down with the force of a small weight pressing on a single point. Then the whole body becomes part of the machine. He braces his 6 legs, arches his back, and pries the other beetle loose. For a heartbeat, his enemy hangs in the air, helpless overhead. Then he is thrown, flung backward off the branch into the leaf litter below. No blood, no kill, just pure leverage and brute structural engineering. This is the shot the whole design was built for. A beetle lifting another beetle on the end of the worst lever in nature. And the only reason it works is the engineering hidden inside his skull. Here is where the beetle stops being a curiosity and becomes a blueprint. Because the problem he solved is the problem haunting modern robotics. A robotic gripper must reach far, hold firm, and never break under load. Reach, grip, and structural safety, the exact three forces fighting in his jaws. So engineers did the obvious thing. They copied him. Researchers took stag beetle mandibles and rebuilt them inside a computer. They used computer-aided design to capture every curve and tooth. They ran parametric modeling to test how each shape changed the grip. They pushed the virtual jaws through finite element simulation to map the stress. The geometry revealed a clean trade-off between grasping power and structural safety. One mandible shape gripped best without tearing itself apart. That winning shape became the template for a real machine. They 3D printed it into a working robotic gripper. A gripper that grabs awkward objects using shape alone, almost no sensors, almost no motors. The intelligence lives in the geometry, exactly as it does in the beetle. The target uses read like a wish list for industry. Grippers for factory automation, sorting strange shapes on a production line. Tools for logistics, handling fragile and irregular parcels. And hands, gentle enough for healthcare and biomedical work. A second team studied the same jaws for soft robotics. Machines that bend and flex instead of crushing, like the beetle's grappling hold. They point to minimally invasive surgical instruments, tools that grip tissue without tearing it. They imagined search and rescue robots, small jaws clearing rubble to reach the trapped. Every one of these is a stag beetle, translated into metal and polymer. And the deepest lesson is not the shape, it is the philosophy. Put strong material only where the load lands, and nowhere else. The beetle spends years as a grub in rotting wood to earn this body. He recycles dead trees, harming nothing, building toward a single summer. Then he flies for only a few weeks, armed, briefly, with the finest weapon he will ever hold. The worst lever in nature, perfected by the patience of evolution, and now, quietly, becoming ours.